Okay, so thanks a lot. So this is the first of 5 lectures of the mini course, The Height of Same Points on Orthogonal Shimura Varieties and Colmez conjecture. So the course is based on a paper by myself, Goren, Ben Howard, and Kirti Madapusi Pera, titled Falting's Height of Abelian varieties with complex multiplication. It's a quite long paper, so I made a selection of a few things that I hope are appropriate for this summer school. By the way, thanks to the organizers for the invitation and the opportunity to present here our work. And actually, I will focus on one of the 2 main results contained in the paper, which has to do with the Colmez conjecture. Okay? So the goal of the course is to explain the strategy, our strategy, to prove an averaged, and today I will explain what I mean by averaged version of Colmez conjecture. By the way, my students always complain about my handwriting, so if it comes to a point that it's not readable, please protest heavily. So we will put, today I will briefly recall what Colmez conjecture is about. It will be pretty elementary. I'm really aiming at explaining things to students. And what we do in the paper is, in fact, prove another conjecture or in fact not prove the full conjecture, but sufficiently many cases of a conjecture of Bruinier-Kudla-Yang. That's the first main result of the paper, and then prove how it implies an averaged version of Colmez conjecture. Okay? So the course will be about reducing the proof of Colmez conjecture to the proof of the Bruinier-Kudla-Yang conjecture, and I'll stop here. So I will not give many details about how we proved those sufficiently many cases that I mentioned. Okay? So essentially, the course is about proving this implication, how you reduce things to get Colmez conjecture from the other one. This itself is a very important, I think, conjecture because it fits in the framework of the Kudla's program. And I think during the week we'll hear something about that as well. So it's an instance, one of the simplest instances of Kudla's program that has been made precise, not simply as a philosophy, but has been precise with the exact numbers by Bruinier-Kudla-Yang. Okay, and before I forget, let me mention 2 things. So first of all, the first remark is that the weaker version of Colmez conjecture that we prove has been used by Jakob Zimmermann to get an unconditional proof of the Andreatta conjecture. So Jakob Zimmermann used the average version of Colmez to get Andreatta. So Andreatta's conjecture characterizes Shimura subvarieties of Ziegler modular varieties as those varieties having a dense set of Zariski dense set of CM points. There had already been, there are two approaches to prove this conjecture. And before the proof of Jakob Zimmermann, those approaches depended on the use of the generalized Riemann hypothesis. Okay? So Zimmermann removed the use of GRH in the proof. And remark 2 is that there is in fact another proof around the same time as us of the average Colmez by Yuan and Zhang, and maybe in the afternoon we'll hear something about that, I don't know. And, but they use completely different techniques, okay? So the techniques that we will use due to our use of the Bruinier-Kudla-Yang conjecture are really about arithmetic intersection theory on some specific Shimura varieties. Instead, the techniques that Yuan and Zhang used have more to do with the arithmetic of Shimura curves over totally real fields. Okay? Okay, so this is as far as the introduction is concerned. What is the eraser? Ah, this one. Sorry, yes. Okay, so I'll now erase this, this blackboard, or at least part of it, and following the suggestion of one of the organizers, simply leave it for the notation, and if I want to state results that I want to keep, and then simply use the blackboard underneath for the lecture. Okay, so this first lecture is about really Colmez conjecture. So I want to explain what it is about and make a first reduction that will be helpful for our strategy. So what is it about? So the Colmez conjecture, so let's fix the main actors, so notation. So notation, we will have a CM field. So E is a CM field of degree 2D, and F inside E is the associated totally real subfield, so only real embeddings of F, and then F inside E is a purely imaginary quadratic extension, okay? And the second actor is A, which is an abelian variety over the complex numbers of dimension D. So this D of the degree is the same D as the dimension of the abelian variety, with an action of the ring of integers OE of E. Idest, we have an embedding OE inside the endomorphism algebra of A, okay? And this will be important. So I'm not assuming that the field E embeds in end 0 of A, so the normal field algebra tensor with Q, but I'm really making an integral statement. So the full ring of integers, not simply an order of E, should act on A. Okay. Then, so we will say that under these conditions, A is an abelian variety with Cm by full Cm by E, or I would simply say A is a Cm abelian variety. And since under these conditions, we know that in fact A is defined only over the complex numbers, but can be descended to an abelian variety over a number field. K. And in fact, again, since A has an action of OE, this abelian variety defined over a number field has potentially good reduction everywhere. Idest, we can assume, possibly after enlarging K, that A is the generic fiber of an abelian scheme over OK. That's calligraphic A. Which also will have an action of O of E. Okay? Okay, good. So these will be our main actors. And what Colmez conjecture is about is the Falting's height, or the modular height of such an abelian variety with full Cm by the ring of integers of the field E. So let me briefly put on the Blackboard a working definition of the Falting's height. Of course, this can be done more generally than simply abelian varieties with Cm, but we'll have a shortcut by the assumption that A has a good model everywhere over OK. That's what we will use now. Okay, so what do we do? So we do the following. We let omega A to be the top wedge power of the invariant differentials of calligraphic A, sorry, omega calligraphic A, first mistake, relative to OK. So it's really also simply this expression. So this is a projective, so H0A omega 1 A over OK is a projective rank D OK module. So the top wedge power is a projective rank 1 OK module. And now if you take a section of omega A, a rational section, which is non-zero, so it will be a basis for this K vector space, then the Falting's height of A will have two contributions, and it will have an infinite part. So then we define H Falting's infinity of A, and this section S that we have fixed. So there is a normalizing factor that will make the definition independent of the number field we started with. And then we'll have the log of the norm of a section S with respect to suitable matrix at infinity of omega A. So this is the log of the absolute value of the integral of x sigma wedge S sigma bar or A sigma C, where sigma k over C run over all embeddings of k, and A sigma and S sigma are the base change of A and S via sigma. Okay, then this is a top degree form on this 2D-dimensional real analytic variety, so I can integrate it and get a number. Okay, non-zero. Sorry. Sorry, it's S sigma. Thanks. Should be S sigma, and I take its absolute value and then the log. Okay. Of the invariant differentials. Of the invariant differentials. Or if you want the global sections of the Kähler differentials of A relative to OK. Okay? Then there is a finite part of this Faltings height of A with respect to the section S that we have specified. And again, there is a normalizing factor coming from the degree of the field. And then we sum over all possible places of OK, so maximal ideals of OK. And then we take the order or pole or vanishing of S times the log of the norm of P. So where ord P of S, it's simply the order of S in. So we take our projective OK module, we localize it with respect to this maximal ideal. That's a free OKP module of rank 1. We take a generator with respect to a generator as OKP module. So it's really the order of vanishing or pole of S. Okay? And finally, we define the Faltings height of A to be the sum of these two contributions, small f, and the remark is that, as the notation suggests, this quantity does not depend on the model A, but that's unique, essentially. It does not depend on the field K that we choose and on the section S. So this definition is independent of S and K or K and the section S that we chose. And remark 2, yes?
So this is because A is semi-stable?
A has good reduction everywhere, yes. So the neural model is really this abelian scheme, calligraphic A that we have fixed, which is independent of base extension. Of course, you need to pass to the level where it exists, but that's what we did. Okay. And remark 2, that we could have been more conceptual and actually use this formula to say that omega A plus this norm on sections at infinity they have defined there for every complex embeddings give metrized line bundle where I denote omega A hat. So it's really the underlying OK modulo omega A plus those metrics at infinity. And H Faltings of A is really its arithmetic degree, maybe normalized. It depends how you define it by the field extension, KQ. Okay? That explains actually why remark 1 is true. And the reason why this does not depend on S is by the product formula. And in fact, this arithmetic degree that I mentioned here is computed explicitly exactly in the way that I've chosen to present the material here. You choose a rational section and see what the metric at infinity gives, what's the order of vanishing or poles of it is, and you sum it up and you get your definition. Okay? Okay. Yes. So this is called, the Faltings height, or Faltings call it modular height. Okay, so we are ready for the first theorem of Colmez. That is the beginning of this conjecture. So I need to move down the blackboard to add one theorem that will stay up there and will not be removed. So I hope I can, unless, anyway, I'll move up very quickly the blackboard again so you can look at the last part of this blackboard. So in Arnold's paper, Colmez, that under our assumptions, the Faltings height, there is one definition that I still need, sorry, so don't copy. So I need also the definition of a CM type. So you see, so you have an action of OE on A, and hence in particular, E, so sorry, if you take the invariant differentials of our abelian variety over C, this is a d-dimensional C vector space, okay? And this decomposes for the action of E into D, which is the dimension of this space, eigenspaces. Okay? And on each of them, E acts via an embedding sigma of E into C. So in this way, you get a subset phi inside all possible embeddings of E into C. So D eigenspaces, they are all different. So this subset is of cardinality D. And it has the property that if you, for every embedding, you compose with complex conjugation on C, you get another embedding, okay? Then for every embedding, if I compose sigma, if I compose with a complex conjugation, I call it sigma bar. And then if you take this subset phi and you take the images of all those embeddings via complex conjugation, as I just explained, this gives the set of all fields embeddings of E into C. So E has degree 2D over Q. So you have a set of cardinality 2D. Phi has cardinality D. Phi bar has cardinality D. And none of those embeddings appearing here appears here. So you get exactly this decomposition on this set. OK? Good. And then I can mention finally the theorem of Colmez that under our assumptions, the Faltings height of A depends only on the pair given by our CM field E and of the CM type phi. So all embeddings of E into C appearing through the action of E on this C vector space. Not on A. Meaning that if you have two complex abelian varieties with full CM by OE, and where this set of same types is the same, okay, these complex numbers that we just defined is the same, okay? And hence, we are allowed to introduce a new definition, a new notation, where we remove the dependence of A from the Faltings height, and we denote H Faltings of E phi this quantity. Okay? Okay, so now I can at least say what Colmez conjecture is about. And Colmez conjecture is about a formula that computes this quantity given a CM field E and a CM type phi. So Colmez conjecture provides a formula for H Faltings of E phi in terms of special values at 0 of L functions of Artin characters and their derivatives. And their conductor. Okay? So before making this conjecture precise, that I hope I'll manage to do, let me give one example for the case d equal 1, which is the Chaulas-Albert formula. Let me give you the version that we will prove, the averaged version, so you will see what I mean, because in that case the formula becomes quite simple. And then we move on trying to analyze what the statement more precisely says, because in that way, we also make an important algebraic reduction that will allow to simplify. And it's one of the ingredients to get our proof. Okay, so example, d equal 1, we get Chawla-Selberg that says that, so in this case, then Q inside E is quadratic, imaginary extension, okay? And the formula, which is equivalent to Colmez conjecture, so in particular, we can omit the proof in the case d equal 1, and we will do that at some point. And the formula gives that the Faltings height of this quantity is minus 1/2 of, so epsilon is the character defining this, of the Golan group, if you want, of Q bar over Q, giving this quadratic extension, okay? On the Adeles of Q, if you want, giving this extension. So the formula is not finished yet. So there is one term where, as I said, you have the special value at 0 of the L function associated with this character. And this does not vanish, so this makes sense. And on the numerator, you get the derivative of this L function evaluated at 0. And then you have minus 1/2 of log of 2 pi. And then you have a contribution coming from the Artin conductor of this character, which is simply given by the log of the discriminant. And note that I can write my log 2 pi again using the same formalism as the usual zeta function derived and evaluated at 0 divided by the value of the zeta function at 0. Okay? So even this term can be interpreted in terms of Artin characters. Okay? So this is the formula that Colmez conjectures, and in fact was already existing before he made a conjecture. In the case d equal 1, and it was under the Chawla-Selberg, the name of Chawla-Selberg formula. Okay? So let me put also on the Blackboard the average version, which you will see has a very similar, it's very similar to the one we have. So average version of Colmez formula or conjecture. So in this case, we take, so the average is, means that we sum over all possible same types these quantities, okay? So let me denote by Cm of E the subsets, so that means Cm types of E, the subset of all possible embeddings of E into C such that phi disjoint union of phi bar is equal to hom EC. So this is the kind of same types that already appeared in our definitions before. And now the formula becomes the following. So up to a normalizing factor, which is 1 over 2d. So if we sum up over all possible Cn types for E of the quantity that Colmez conjectures should be computable in terms of L functions, this becomes the following. So let me first of all write it in a similar way as I wrote it there. there's a log outside of dE divided by dF, and then minus the half of log of 2 pi. So you see it's very close to the one I wrote before for the Chaulas-Selberg case, where dF and dE are the discriminants of the total real subfield F and E respectively, and chi is the characters instead of the ideales of Q, in this case the ideales of F, character defining the Galois extension F inside E. Okay? So the kernel is the norm from A E star, and it identifies the quotient, which by class field theory is the Galois group of E over F with plus or minus 1. To that you can associate an L function. Again, this L function does not vanish when you evaluate at s equals 0. You can take its derivative and evaluate it, so you get a logarithmic derivative of this L function. And then you have a contribution from the zeta function of Q as before. It's exactly the same up to this dimension that appears. Then you have a contribution that measures ramifications like arcing conductors, which in this case is given by the discriminant of E divided by the discriminant of F. Okay? So it's very like the formula that we computed. Okay. So maybe let me put this formula. I'll simply rewrite the formula here. So average Colmez, so 1 over 2d, the sum over all CM types of the Faltings height of E phi should be equal to this quantity. And this is what Zimmermann used. Okay? Why? Because now, so Zimmermann had the problem of bounding Galois orbits of CM points that he could do using, if he could control the Faltings heights of these CM points. And via this formula, he managed to control it using classical analytic number theory, because special values of L functions and their derivatives and so on can be computed and controlled. Okay, so that's where sort of it's exactly this link that allowed him to use techniques from classical analytic number theory to get the bounds that people were hoping for and could be deduced before him only using GRH. Okay, so that's the formula that we want to prove. But before moving on, let me say something more about Colmez conjecture and try to be more precise about the general statement, because in fact we will need some further analysis of the Colmez conjecture and techniques to make a further reduction that will make the proof of the average Colmez easier, okay? And maybe I can say it right away. What I want to prove is that this left-hand side can be computed as the Faltings height of a different object, a different pair, which is given by the reflex algebra associated to E and the reflex CM type. Okay? I'm going to explain what these objects are. Okay, so let me try to make Colmez conjecture more precise. So we denote by, so we fix once and for all embeddings Q inside E inside C. And the embedding of E into C, we call it iota 0. It will be important. So it's one of the embeddings that already appeared. And we also let QCM be the composite of all CM extensions of Q in C. We'll let calligraphic G the Galois group. This is a Galois extension of Q. And inside it we have, for this field, a well-defined automorphism, which is complex conjugation, which is central, which I call C. Which for all CM extensions really acts on the field as the complex conjugation. Okay, so the starting point of Colmez analysis is the following Q vector space. So I will denote by CM naught the set, the Q vector space of locally constant for the profane topology on G, locally constant in the discrete topology on Q, central functions from G to Q. So central meaning that they are constant on conjugacy classes. Such that, and that's the extra requirement that I make, that for every that central functions, let me say A, okay, such that if you evaluate A at an element little g of G, and you sum the evaluation of A at G composed with the complex conjugation C, this should be constant. Is constant for G varying in the Galois group G. Okay? So let me forget this extra assumption for 1 second. And let me remark that we know that if we take the complex vector space of locally constant central functions from G to C, this is, by a well-known result, can be written as a C linear combination of artin characters. So you see already that there is a relation to artin characters that appear in the formulation of Colmez conjecture. Okay? So any such A can be uniquely written as a finite C linear combination sum A eta of artin characters that are central functions from G to C, locally constant. Okay? So if I base change to C, I have this very natural basis. This assumption that I will denote with a cross here, the fact that AG plus ACG is constant, means that the characters, if you take a character appearing in this decomposition for A eta different from 0, and you take the sum of this character with eta composite complex conjugation, okay, this should simply give, since the decomposition is unique, should really simply give many times, which is this constant here, right, of the trivial character, okay? So this condition here says that my function eta, if non-trivial, if A eta is different from 0 and eta is different from the trivial character, then the value of the arithmetic character on complex conjugation is minus eta, the identity. So it's a totally odd character, which in particular implies one of the conditions that already appeared to make sense in Colmez conjecture, the fact that if you take your arithmetic character, you take the L function and you evaluate it at 0, this is not 0. Okay? So this condition singles out essentially those characters which, if non-trivial, satisfy this condition, as they are totally odd. Okay? So the next step of Colmez is to cook up, starting from a CM field and a CM type, a function in CM0. Okay? So given E phi, we get a function A not E phi in CM0. And it's almost lunchtime, so it's time for a recipe, right? And so the recipe is the following. First of all, for every G in G, I define A phi of G, so there is no not. So the function that we'll be interested in will be a modification of the one I'm defining now, as simply the cardinality of my CM type phi intersected with the image of my CM type via an element of the Galois group. Okay? So every embedding of E into the complex numbers, of course, by the way I define QCM, factors via QCM, right? So given embedding of E into QCM, you can compose that embedding with an element of the Galois group, and you get another embedding of E into QCM, right? If you do that for all the embeddings appearing in the CM type phi, you get a new CM type. Okay? Great. So you simply measure the cardinality of this set and the translated subset, where the intersection happens inside, of course, all possible embeddings of E into C. Right? Great. So notice that A of E phi of G plus A E phi of CG, well, it's simply the image, since C is a central element, it's the intersection of phi with G phi and its complex conjugate. But this covers all the automorphism group. the homomorphism of E into C, this is simply the cardinality of phi, which is D. So this condition here that the sum is constant is meaningful in this case, and it's easy, right? The problem is that this is not a central function, so I cannot feed it in the machinery. And to fit in the machinery, I have to massage the function so that it enters the machine, right? And I do it in a brutal way. I simply take the average of over all conjugacy classes, right? So after the recipe, we also massage. And we define A0 E phi G to be, well, 1 over index of the stabilizer of phi. So we said that the Galois group acts on these CM types. So I take simply the stabilizer. So those elements that sense the CM type phi into itself. And then I sum up over all sigma in this quotient set of the function, well, yeah, that I've just defined. But I make sure to translate this same type. Okay? So in this way, I have this condition for granted because it's true for every single one of those elements. And I also made sure that this function, which is also locally constant clearly, it's central. Okay? So maybe I leave this definition here. So then my A0 E phi lies in CM0. Okay? So I can write it as the sum of A eta eta as before. Okay, using artin characters as a basis for the C vector space spanned by those functions. And now Colmez conjecture states that the Faltings-Height of E phi should be computed using this function and its decomposition as a C linear combination of artin characters. Okay? So this should be the sum over all etas appearing here. The coefficient A eta comes out. And then for every eta appearing here, I have two parts in my expression. The one, actually I should put maybe a minus before that. Two parts that resemble the formulas that we have already seen in the Chaulas-Albert case and in the average case. So you take the derivative of the L function associated to eta, the logarithmic derivative, plus the log of the artin conductor of eta. Again, I have now defined the L function. I'm not going to define the artin conductor. It simply measures how ramified your character or the representation associated to the character eta is. Okay? So it singles out the primes where the representation does not factor through inertia, et cetera, et cetera. And then it measures how wild or tame it is. Okay? So even if you have not understood the formula, and actually I don't know how Colmez got it even, based on which intuition, the principle is you have your pair given by the CM field and the CM type. You associate a bizarre looking function, which is this A naught E phi. You use its expression as a combination of ardent characters to cook up a number which give up to the multiplicities or the complex number, these scalars that appear in this decomposition. You get a combination of logarithmic derivatives evaluated at 0 of your arcing characters and arcing conductors of these characters. Okay? Maybe just last 5 minutes to make a further reduction. So what do we get from Colmez formalism? From Colmez, you get that if you sum up to some multiplicities, which is in this case the degree of E over Q, these functions, and you sum up over all Cn types, okay? So for every pair E phi, I've associated a function. Now I sum them up over all phi for fixed E, okay? This is equal in Cm0 to 2d minus 2, the trivial representation, plus 1 over d, the induced representation from the Galois group of F to the full Galois group of QCM over Q of the character chi. So remember that we have associated a character to our extension F inside E. Okay? So that's the key that appears here. I induce the character, and you can prove, in fact, that you have an equality of functions. Once you have an equality of functions, since the way Colmez associates a number to your Faltings heights, it's linear in the combination of the arcing characters appearing, okay? If you want to compute what this number is when you fit it in this machinery, you can simply take those formulas applied to the right-hand side, okay? And then you see that you have up to the multiplicity 2d minus 2, you should have the derivative of the L function associated to the trivial representation, which is the usual zeta function, its logarithmic derivative, right? And in that case, there is no arcing conductor. And that is exactly what appears here, because we said that this is exactly the logarithmic derivative of the zeta function, okay? And then you have to compute this square here for the induced representation. But then you know that the L function for the induced representation of a character, it's simply the L function for the characters, but for the fields from which it is induced. Okay? So this contribution for eta, the induced representation from the character chi, is exactly on the nose what appears here. The logarithmic derivative of chi. This L function is computed for F, right? while here the formula is for Q. And then you have the Artin conductor for the induced character chi, and this is exactly what appears here in the middle. Okay? So using this formula for the right-hand side of this equality, you exactly get this way. We get the average formulation of Colmez. Great. And I think I'll simply stop here. Tomorrow, I want to make another reduction based, again, on Colmez formalism, where I replace, as I said, the left-hand side of this equality, this sum, simply as the H faltings of E sharp, phi sharp. So we'll define a new CM algebra E sharp, the total reflex algebra, a new CM type, and prove that its faltings height is equal to that sum. And then the formula that we'll prove is exactly simply the faltings height of E sharp, phi sharp is equal to what appears on the right. And tomorrow, I will also explain the overall strategy, how to get it. And then we'll have to roll up our sleeves and work. Thanks.